All right, so last time we talked about angular velocity. Angular velocity, describing the rate at which something rotates over time. In this video, we're going to talk about angular momentum. So angular momentum is a conserved quantity. That's why we care about it. It's analogous to linear momentum in that it is the rate of change of something scaled by something like a mass. And what it tells us is roughly how difficult it is to stop something that is rotating. So if something has a lot of angular momentum, it's kind of hard to stop. In the same way that if something has a lot of linear momentum, it's kind of hard to stop. It's hard to stop a car, right, that's moving at 20 miles an hour. It's not that hard to stop a fly that's moving at 20 miles an hour. So angular momentum tells us roughly how hard it is to stop something rotating. All right, let's jump into it. Okay, so angular momentum. What is it? All right, formally, we write it out like this. Angular momentum is omega, the angular velocity, scaled by this thing I, the moment of inertia. We're going to talk about the moment of inertia a little bit more in a second. Here's something to note about angular momentum. Angular momentum always points in the same direction as angular velocity. So L always points in the same direction as W. This number I is always positive. I don't mean for these to be minus signs. I'm just highlighting L and omega. Okay. So since I is always a positive number, L always points in the same direction as omega. If I have my rotating disk, here we go. If I have my rotating disk, it is rotating with some speed, some angular velocity omega. Boom. Intuition check. If omega is pointing up, am I going clockwise or counterclockwise as viewed from here? So this is counterclockwise. This is clockwise. Which direction is it? This one. It's rotating this way. Double check with your right hand rule. So it's rotating this direction if this side of the disk is closer to me. It's like a donut that I'm drawing with the side closer to me. Okay, so my omega points upward. My angular momentum is also going to point upward in this case. So here's my L. L is just a scaled version of omega. So here's my L. Boom. Okay. The units of angular velocity. Not units of angular velocity. Goodness, I'm tripping over myself today. Units of angular momentum are kilogram times meters squared per second. Okay, now if you contrast this with the units for linear momentum is just kilogram meter per second. So the difference between angular and linear momentum in terms of units is just a meter, right? Instead of it being a meter, it's a meter squared for angular momentum. Okay. The last thing I wanted to hit is that two objects can have the same omega and a different angular momentum. So for example, say that I've got my CD-ROM versus one of those big old vinyls that your parents or grandparents have. So a big old vinyl, let's say it weighs more, it's heavier, right? And it's also more distributed. It's got more width to it, more breadth, I guess is a better way to say it. It goes out farther. So this thing is going to have a larger moment of inertia. It's gonna be harder to cause to rotate or stop rotating. So for the same omega, it's going to have a larger L. So it's rotating at the same rate of, let's say, like 2 times a second or whatever, the same rate as this CD. If they rotate with the same rate, the angular momentum of the one that has a greater moment of inertia will be larger. Okay, I think that's all I really wanted to say introducing angular momentum initially. So in order to understand this equation a little bit more fully, we're going to need to understand this I a little better. So the moment of inertia I is formally defined by this obnoxious little equation. Here it is. So I, it's not a vector. I is the sum of all the little spots that are massive, all the masses, times the displacement vector magnitude to that position squared. Yuck. So what does this mean? It means that if I look at all of the little massive points, if I take a look at all of these little massive points going around my record or whatever, and I draw a little vector to each of them, r, from my pivot point, the length of that vector r times the mass itself, the little glob of mass here and the little glob of mass here, etc. I sum up all of those little contributions for the whole surface, the whole object, and that sum gives me I. Now we're not going to ask you to actually do that for solids, because, like a solid object, because that involves integration. It's just a little bit too complicated. We may ask you to do it for points. So for example, if I had, let's say, 2 yo-yos, each of mass m, here's yo-yo 1, here's yo-yo 2, yo-yo 2, there we go. And each of these yo-yos, let's say, are connected by the same length r, just for fun, although in general they can be different, r1, r2. And they each have mass m1 and m2. Then the moment of inertia of this system of yo-yos that I've attached to this pivot point, how hard it is to make them, how do I say this? How hard it is to make them as a system slow down or speed up, I would be m1 times the magnitude of r1 plus m2 times the magnitude of r2. So again, the exact form for how to calculate this, I would just write this down. The intuition I want you to have is that the heavier and more distributed the object is, the harder it is to influence its rotation rate. And that's always measured relative to an axis. So for a pencil, it's really easy for me to rotate the pencil this way, because the pencil is not very distributed around the axis of rotation. So if I look down this axis of rotation here, straight through the middle of the pencil, all of the mass of the pencil is concentrated around that axis. It's not very distributed around it. If I rotate my pencil so it's like this, and now I'm rotating it around the, say, the center of mass of the pencil in this direction, now lots of the mass of the pencil is way far away from my pivot point. So the moment of inertia here is higher. It's larger. It's harder to rotate something this way than this way. And a pencil is kind of hard to show just by feeling it, but if you've got a piece of pipe lying around or a bat or something like this, it's a little bit easier to see. So feel free to try that on your own. Okay, you can see here some common moments of inertia down in the slides. This image was shamelessly ripped from Hyperphysics, all hail Hyperphysics. So notice that for each of these objects, the value of the moment of inertia, I, depends on both the axis of rotation and on the object itself. So like for this rod, right? If I rotate my rod about its center, my I is 1/12 of the mass times the length of the rod squared. If I rotate the rod about the end, so if I rotate the rod about its end, like the eraser of the pencil instead of the middle of it, say, if I rotate it about this, then my moment of inertia is much larger. It's actually 4 times larger. Okay, so again, intuitively, the moment of inertia increases with greater mass and when the stuff is more spread out away from the axis of rotation. Okay, so why do we care about any of this stuff? Who cares about these I's and L's and W's, man? What's the point? So the point, why we care about angular momentum, why it matters, is that it turns out it's a conserved quantity. So we'll see that using angular momentum, we can figure out what happens when, say, 2 rotating asteroids hit each other. Or, I don't know, say like if you've got a more complicated pool table and now the balls actually rotate, you can figure out how the balls will rotate going forward after collisions and such. So conservation of angular momentum lets us figure out how rotation transfers between objects. It's a little bit less intuitive than the linear case, but equally true. Both are conserved. Okay, so what I want to do with this last moment of this lecture is talk through our concept mapping so far from the linear to the angular case. So angular velocity, omega, corresponds to something like linear velocity. They both describe rates of change of something. In the angular case, it's the angle, theta. In the linear case, it's the position, say x. Angular momentum, L, corresponds to linear momentum, P. Linear momentum is just velocity scaled by mass. Angular momentum is just angular velocity scaled by moment of inertia. As a result, moment of inertia is kind of like mass. It just tells me how hard it is to change something's angular velocity. Yeah, angular momentum, same thing. So yeah, the larger something's moment of inertia is, the harder it is to change its omega, its angular velocity. The larger an object's mass is, the harder it is to change its velocity. What about force? What's going on with force? That's for next time. You'll have to stay tuned.